Today I want to talk about a very important industrial technology of the last half of the 20th century, the technology for making integrated circuits. These are the backbone of modern electronics. They're what have brought you low-cost computers and a variety of electronic controls spreading to almost all parts of industrial activity and in everything around the home. This technology has been very powerful. It has allowed us to reduce the cost of electronics dramatically over the last few decades. In fact, today you can buy an integrated circuit containing millions of transistors for the price of a single transistor when I first got in the business in the late 50s. I know of no other technology that has made million-fold reductions in cost. This is one of the things that has made it so powerful. In fact, to use an analogy, one I've used quite often, if the auto industry had progressed at the rate of the semiconductor industry as a result of this technology over the last 35 years, today you could buy a car that would travel comfortably at several million miles an hour, get 1,000,000 miles per gallon of gasoline, and would be more economical to throw away your Rolls Royce and buy a new one than to park it downtown for the evening. I thought that was pretty good until once somebody in the audience pointed out to me it would only be about 1 inch tall and 2 inches long. It wouldn't be much good for your morning commute. Recently, this analogy was updated by Professor Jeffrey Raport of Harvard and applied to the aircraft industry instead. By his calculations, a Boeing 767 would cost about $500 and would circle the Earth in 20 minutes using 5 gallons of fuel. Clearly, there's something unique about this semiconductor technology. To me, what we're doing is exploiting a violation of Murphy's Law. By making things smaller, everything gets better simultaneously. The circuits become higher performance because the transistors, as they become smaller, will operate at higher frequencies. The power consumption drops considerably. Systems become much more reliable. But most importantly, the cost of doing things electronically drops dramatically. Let me show you a couple of the early devices that were really the beginning of this technology. First, what I consider to be the beginning, the planar transistor. This picture shows a top view of a single transistor structure that covered a silicon wafer in those days about 3/4 of an inch in diameter. There were tens of these identical transistor structures on the silicon wafer. And beyond this stage, they got cut up into individual transistor structures, wires attached to the 2 aluminum electrodes that you can see here, the one in the center and the circle of light-colored material with the little blob on the corner of it. The third contact of the transistor being the bottom of the piece of silicon where it was soldered onto the package material. I have a fond recollection of this particular device since it's probably the only product I ever designed personally that went into production. The peculiar dimension, 764 microns, reflects merely the fact we used to work in the English system, and this was 30,000th of an inch. This is the conversion from English to metric that gives the unusual number. The next slide shows the first planar integrated circuit made at Fairchild Semiconductor in 1961. I'm sorry that the picture that's been preserved was such a bad example. Clearly this one is quite dirty, and the pads around the edge to which the connections were to be made are fairly badly damaged in the process of etching the round piece of silicon so it would fit in the package, the kind we used at the time. These were the first 2 examples, the basic technology that I'm going to be describing. The planar transistor gave us a structure where we could interconnect devices by running metal films up over the sensitive parts of the transistors called junctions and could connect one to the other. The idea of the integrated circuit was developed initially, I guess, at Texas Instruments, where Jack Kilby built an integrated circuit. And then at Fairchild, where Bob Noyce had the availability of these planar transistors, he saw how to extend that technology to make a practical integrated circuit, and that has been the basic technology that has been evolving ever since. In the early 1960s, I was asked to write an article for the 35th anniversary of Electronics magazine, in which I was supposed to predict the course of semiconductor components over the next 10 years. In that, I took the existing integrated circuits, there were only relatively few at that time, looked at how the complexity had been increasing and thought that was a trend that was going to continue, and I drew the curve that is shown in the slide. This extrapolated from the most complex circuit with something like 60 transistors and resistors in it to something that would be 1,000 times as complex by 1975. This 1,000-fold extrapolation corresponding to a doubling of the number of components in an integrated circuit every year was what got termed Moore's Law at some later date. Now, Moore's Law has been applied to a lot of other things, and I'm happy to take credit for all of them, but this was really the origin of that idea. Well, the next slide shows a sprinkling of some of the more complex devices that were built during that decade, and as you can see, they track the line really quite closely. Certainly much better than I could ever have expected them to do when I originally published the curve. The most complex device was within a factor of 2 of the 1,000-fold increase in complexity that I had predicted. Clearly, the technology was extending quite rapidly and had a long way to go. Now, it is useful to look at this and to say, what changed in the technology that allowed this huge increase in complexity? And of course, with the increase in complexity, the decrease in the cost per electronic function, since we could sell an integrated circuit for not much more than the price of the individual transistor. This curve can be resolved into a few different contributions. As you see on the next slide, during this time period, the size piece of silicon, the die size as we call it today, that is the size of the little square into which we cut the round wafers, grew somewhat in area. It also grew exponentially, but was nowhere near the 1,000-fold growth that we saw for the complexity of the device. So something else had to be happening. We had to be increasing the density of electronic circuitry on the silicon wafer. That is, we had to be able to pack more transistors and resistors in the same amount of real estate. And indeed, that's what was happening, again, as a result of more than one factor. The next slide shows what happened just because of the process density. As I mentioned earlier, this technology makes finer and finer features to get all of the benefits that we've described. This shows the result of making finer features in increasing the density of the components on the wafer. It goes, obviously, as the square of the linear dimension. Since the line width and spacings weren't always the same, we've used the average rather than the individual numbers on the ordinate. The abscissa showing time. And again, if you neglect the first point, which was the first planar transistor, it falls quite well on an exponential curve. And that first point can legitimately be neglected because on the first planar transistor, we had a lot of other problems to worry about. Working at the minimum dimension was not one of the things we considered important. Now, we have two things now. We have the increasing size of the die, and we have the decreasing size of the features on the die. We can compare those two contributions to the total of what happened during this time period. As you see on this curve, where I've plotted, first of all, each of the two contributions separately, that is, that due to the increasing die size and that due to the reduction in dimensions. You can take those two curves and add them, or since this is a logarithmic scale, we're really multiplying those two effects. And we get this intermediate line, the product of die size and dimensions. And you see, while it accounts for something like 2/3 of the increase in the complexity of the circuits, there's still a significant chunk left, which I've ascribed here to device and circuit cleverness. That is, people learned to design circuits that packed more closely on the piece of silicon. It was room that was left for invention. Now, I had done this in 1975, and looking forward, one thing was of concern. While we could still see increasing the density by making smaller dimensions and increasing the die size, the room for this cleverness had really disappeared, because the last point plotted for 1975 was a particular kind of a device that packed transistors as closely together as they would fit geometrically on the wafer. There was no more room for cleverness. So at that time, we predicted that the slope would change, and we would no longer be doubling every year, but it's something somewhat longer than that, corresponding only to the other two factors that we had available. Still, though, this is a very rapid rate of progress in a technology and allows the complexity of the circuits to double every year and a half rather than every year, slowing down the rate of progress somewhat, but still maintaining something that is unprecedented with any other industrial technology that I can find. What's happened since? The next slide shows the die size history up until the present time for both microprocessors and for the large volume dynamic random access memories that are prevalent in most computing systems today. This continues on the same slope as the line from the early 60s through 1975, suggesting that nothing has really changed in our ability to make larger and larger silicon die economically. This trend has continued. Similarly, on the next slide, we see what has happened on the increase in density due to line widths. Here again, the slope has continued the same as it was previously, with the average line width decreasing about a factor of 2 every 6 years. The same trend that we've been on since 1960. So the increase in circuit density should proceed as it did previously, with only the factor for cleverness removed. The next slide shows what I calculated for a 1975 update of Moore's Law. Unfortunately, it's not what I published, because I thought things were going to carry on a little further with a contribution from cleverness. There was a good technical reason why it didn't happen. The devices I was looking at turned out not to be practical, having some fairly fundamental problems. But the calculation shows that the line is very close to what was actually achieved over this period, tracking with the most complex devices, the DRAMs, tracking very closely the calculated curves. Now, the question looking forward is, can this be expected to continue? What has to be done for it to continue? And let's look at a little bit of those things. First of all, for it to continue in this line, we have to obviously be able to continue to make larger and larger dice and to continue to reduce our feature sizes. But we get to the point where there are several other considerations that we also have to consider as we look at the evolution of the technology. For example, in looking at microprocessor technology, here's a list of a few things that has to be taken into account, as well as just the sheer complexity. Performance is one of the major drivers for pursuing new processors, and performance requires that several things be considered. For example, the transistors themselves have to be made faster and faster, which happens fairly naturally as we go to smaller dimensions. But increasingly, we have to worry about the interconnection structures, how their performance affects the performance of the total circuit. And of course, how close we can get things together, the density of things on the circuit itself. Reliability is extremely important. We have to be sure we don't get to a region where our lines are so narrow or our layers so thin that we have problems with the basic integrity of the structure. And we have to worry about high volume manufacture. This has become a very important industry. Products are made in millions, tens of millions, and even hundreds of millions for certain kinds of devices every year. And the economical and repeatable manufacture is something that is always a major concern, and one that is increasingly a consideration. Let's look at a few of these in somewhat more detail. First, let's take the minimum feature size, the thing that's necessary to keep us on this curve, continuing to violate Murphy's Law. This shows Intel's minimum feature size over an extended period of time, mostly on processor rather than on memory devices. And it shows the roadmap that was laid out by the Semiconductor Industry Association, suggesting how this is going to continue to go over the next several years. As you can see, the slope we've been on tends to continue. In fact, it's extrapolated at least into the early part of the next century. This corresponds to the halving of the minimum dimension every 6 years. And since technology generations, that generally takes 2 technology generations to make such a halving of the minimum dimension. These steps we show here as points correspond to something that is about the square root of that. So every one of these steps between die, every technology generation, say for example from the one shown above about 1989 to the one shown above 1992, cuts the area a given function requires in half, since if you square that square root of 2, you get the factor of 2 that corresponds to the shrinking die size. I'll show that a little more clearly later on. Now, there are a lot of concerns one has to have about the ability to continue this. Some technological and some that relate to the basic physics of the devices. For example, do transistors continue to behave as transistors as the minimum dimensions get of the order of tenths of microns? The production devices today are around 0.35 microns minimum dimensions. This predicts a continuous improvement down to the range of perhaps 0.18 and maybe another generation to 0.13 microns. Laboratory devices have been made that show the electrical characteristics still are useful for making circuits in this dimensional range. It becomes more questionable as one gets down to around 0.03 or 0.05 microns. There it appears that some of the physics may actually make the devices so they cannot be produced as part of a major circuit. But that gives us a long time to worry about that. And frankly, I'm more worried about the technological problem than I am about the basic physical limit in this case, because making these narrow features is increasingly difficult. At one time, it was generally accepted in the industry that it would probably not be possible to make these structures by optical lithography, the standard production technique, below about 1 micron. We were using light of wavelengths around a half micron, and getting the high resolution required over a large field size we thought might require using dimensions twice the wavelength of light. In fact, we have been able to pass that 1 micron barrier without ever seeing a change in the slope of the curve. This was done partially by using shorter wavelengths. We've moved to ultraviolet, and we'll move to increasingly hard ultraviolet as we move down the curve. But at least as big a contributor has been the progress that's been made in optics. The systems that do this today use the state-of-the-art in optics. These are huge lenses or very sophisticated mirror systems that allow us to make structures over very usable areas where the structural features are of the order of a wavelength, and in some cases, by taking special precautions, less than the wavelength of light. We have to continue to push in that direction to stay in this curve because, frankly, once we can no longer use optical lithography, we're faced with some choices that are not very attractive. In fact, we have about 3 equally unattractive choices. The use of X-rays, the use of direct electron beam writing, or the writing with ion beams, all of which will increase the cost dramatically and will negate much of the learning that we have accomplished over this period of time using optical lithography. Staying on this minimum feature size curve is one of the real challenges for the industry. To show you what some of these little devices look like, the next page shows a cross-section through a production transistor today. This is a transistor made with a 0.35 micron technology and is used in making Intel's most advanced Pentium and Pentium Pro microprocessors. The silicon substrate is the pedestal upon which the various features are sitting. Actually, the only part of the silicon wafer that's really active in these structures is the top micron or so. The rest of it just acts as a mechanical support for the structure. The 2 heavy pillars that you see, one on either side of a central structure, are plugs of tungsten that are used to make contacts to the source and drain of this MOS transistor. The gate electrode being the little structure on top of the center feature. The caps on top of the tungsten pillars are aluminum interconnection lines that run in or out of the picture in order to hook this transistor to the rest of the circuit. The entire gray area surrounding the tungsten plugs and the silicon substrate is silicon oxide, which in this scanning electron micrograph shows up as rather featureless. If we move to the next generation of technology, or in fact two generations down, to the kind of things that are just being made experimentally today, you see the transistor on this slide is showing 0.18 micron minimum feature size and the related structure. This is really pushing our capability now. In fact, this is laboratory capability, and it will be several years before this can be done reproducibly in production. I mentioned that more than just density was important in looking at technology appropriate for processors in the future. The next slide shows, for example, how performance is affected by the transistors and by the interconnections. As you see, the performance of the transistor continues to improve. That is, the delay time related to the transistor gets shorter and shorter as we go to smaller and smaller minimum dimensions. On the other hand, the delay time, and the delay time I'm talking about here for the interconnection, is that for a 2 millimeter line connecting devices on the integrated circuit increases. Now, up until the current generation, which is the 0.35 generation of technology, the delay from the interconnects is still significantly less than that from the transistors. While it has to be taken into account, it's not yet the limiting factor. As we move to the next generation of technology, however, at a quarter micron, the delay from the interconnection starts to dominate the delay from the transistor. And looking at a little further in time, far dominates. So it's something that requires a tremendous amount of attention in continuing to evolve the technology so we can take maximum advantage of it. The reason the interconnect contributes this delay is that as we make smaller and smaller features, to take advantage of them, we have to make narrower and narrower interconnection lines. As we do that, the resistance goes up. Even if we keep the thickness of the film the same, as the line becomes narrower, its resistance increases. And as they get closer together, the capacitance from the line to its neighbors also grows. So the RC time constant, the resistance times the capacitance of these lines, is what limits their performance. Obviously, there's an opportunity here to look for materials that lower the resistance or lower the capacitance. It's hard to find them. Typical interconnections are made of aluminum. There are better conductors than aluminum, for example, copper and silver, but they present tremendous technological problems, and neither has been satisfactorily incorporated into reliable integrated circuits. Similarly, with respect to the capacitance, there are materials with lower dielectric constant than the silicon dioxide, but not much lower, and they require abandoning a lot of the technology that has developed here over the decades. Not an easy change to make for a small incremental improvement. There is one thing, however, we can do, though. We can work hard to keep things close together. And one way to do that is to increase the number of layers of metal. So instead of running distances in one layer, we can run up into an upper story, along, and down again. The next slide shows a modern structure. In fact, this structure is actually the one we use in our 0.35 micron technology. The silicon shows just barely at the bottom of the picture. The section on the right shows 4 layers of conductor, labeled M1 through M4, with the intervening plugs, typically of tungsten, that connect one layer to the other. This technology for the multi-layer interconnection has moved very rapidly over the last several years, primarily as the result of a technology called planarization, where we're able to restore a flat surface between each series of steps. So we're always working on a surface where we don't have to be too concerned about things like depth of field or about films running up and down some topology that might be relatively difficult. This will continue to be an approach that will help alleviate the problems of performance relating to interconnections. It will allow us to increase the density. But what it does is complicate the process considerably. Each of these layers of metal has an underlayer that makes the metal interface to the insulator work well. It has the basic aluminum layer, or an aluminum copper alloy typically, and then special metals to make contact to the tungsten and one thing and another. So the number of process steps grows dramatically as we add layers. But the benefit of being able to maintain the very high density and to continue to increase it certainly justifies movement in this direction. Another problem we have to contend with is one of the minimum layer thicknesses that we use in the technology. In particular, concern about the minimum insulator layer. This is also an important parameter in determining transistor performance, and it's one where we actually are approaching some sort of a physical limit. I've taken this data from something published by Professor Mead at Caltech, and he shows a point that is sub-10th micron and about 30 angstroms of being in production. I don't know where that's produced. That's certainly far beyond anything we're doing in both respects. On the other hand, this trend is one that the industry has been on for some time. While it looks like the trend toward always narrower lines as the minimum feature size, it has a real physical limit that relates to quantum mechanical tunneling. At 50 angstroms, at a few volts, electrons will tunnel through a material, so even a good insulator like silicon oxide will actually show up as conducting. The rate of tunneling increases exponentially as the thickness decreases. So at 30 angstroms, tunneling is a very important problem and is something that has to be contended with at even very low voltages. Now, in fact, we've utilized this to make some special kinds of devices where we actually tunnel through the insulator in order to charge or discharge electrodes. On the other hand, for conventional transistors, it's a problem, and the kind of thing that requires us to take precaution. Probably the precaution will be that the layers will tend not to get any thinner than this. Of course, you have to recognize that a 30 angstrom layer is only a few atomic layers thick, maybe 5 to 10 layers of silicon oxide. So we're really getting down pretty close to the atomic nature of matter. Clearly a fundamental limit there. On the other hand, we can continue to exploit the other improvements on the technology, such as decreasing feature size, even though we're getting down in a range where we can no longer decrease the thickness of the insulator. As we increase complexity, other things happen. There's a lot going on in a microprocessor with 10 million transistors. This requires a fair amount of power, and indeed the power consumption has grown as the complexity of the devices have grown, partially just because of the increase in the number of transistors that have to be active, but more importantly because this gets combined with an increase in frequency. And the power consumption in these devices is typically that of charging capacitors and then discharging them to ground. So you get kind of a CV squared impact on the total power consumption. That is, if the capacitance goes up, the total amount of stuff on the chip goes up, the power increases, and as the voltage squared, so the voltage at which the circuits operate is clearly an extremely important parameter. This curve shows that processors today are dissipating of the order of 20 watts, and indeed that's what Intel's leading edge processors do. The extrapolation is what the Semiconductor Industry Association roadmap suggests we should be able to do looking forward. Now, it takes a lot of work to achieve even this, and the last point out here is nearly 60 watts, an awful lot of power to get out of a package containing one of these processors, and a real problem for things like laptop computers, where batteries can't support 60-watt processors for very long. In order to stay on this curve, it's necessary that we scale the voltage of operation. This was almost a constant for many years. 5 volts was the standard operating voltage for the families of integrated circuits that were used conventionally. And from the 60s clear into the 90s, 5-volt operation was where almost all products were designed. As we got into these power problems, however, the attractiveness of scaling voltage became higher and higher. And also, by scaling voltage, we could take advantage of the decrease in feature size, since the ability to support voltages decreases as we go to smaller and smaller structures. We've taken the step now from 5 volts to 3.3 volts and expect to see it step down fairly rapidly to some kind of an ultimate limit. While there's no fundamental limit we can point to clearly, the engineering consensus seems to be that somewhere around 1 volt is where this will stop being productive. Indeed, getting from where we are to reliable, high-performance 1-volt circuit requires a lot of really good engineering. There's a lot still to get out of the technology, but we have to look at a lot of directions simultaneously. Here I've talked about a few of the technical ones. Now I want to change over and talk a bit about some of the economic ones. In particular, let me talk about cost. There are a variety of things that contribute to the cost of a microprocessor or other complex integrated circuit. There's certainly the design cost, the product cost, and then the ongoing support cost. I'm going to say a little bit about each of these. Certainly the cost to design these products has not gone up as fast as the complexity, but it has gone up at a significant rate. Where we've increased the complexity orders of magnitude, we've only increased the design cost by a fraction of that because of the improvement in the computer aids that we use. On the other hand, the design of a modern microprocessor can be several hundreds of millions of dollars now. If only a small quantity is made, that design cost amortized across the whole production life of the device can be a significant contributor to the total cost. For example, if you spent $200 million to design a microprocessor and only made 200,000 of them over the lifetime, which is a large number for a processor dedicated to a single application or a single company, the cost of the design alone adds $1,000 each to the microprocessors that have been built. A huge increment when you look at personal computers selling for less than that. Similarly, the design and engineering for the production process is in the multiple hundreds of millions of dollars range this time for each of these generations of technology. Not counting the cost of replicating that technology to build it in volume, just the cost of the engineering necessary to bring it to fruition. Product cost, we have to look at a variety of contributors. The cost of the piece of silicon itself, the die or the silicon chip, the cost of the package and packaging, the cost of testing, and then these things always require some ongoing support. Let's look at a couple of these things in more detail. This shows the relative cost for developing generations of microprocessors at Intel. You see that the Pentium Pro is well over 100 times the cost of developing the 8080 in the early 70s. And that the cost per generation is something like doubling. I suppose here's another corollary to Moore's law that I ought to expound upon, but I don't plan to at this time. This is only one of the factors of the one-time cost we have to consider. But I want to spend more time talking about the cost of practicing the technology itself. That is, the economics of building these batch-produced devices. By batch produced, I mean the case where we take a silicon wafer and we cover the entire silicon wafer with identical structures, so that in the process of building one of these structures, we build tens or hundreds of them, so that the cost of processing the wafer can be amortized over all the good chips we get out of that wafer. Then these get cut up and packaged individually. And I want to take you through a very simple model of how this works, so you get an idea of the kinds of things we have to be concerned with in practicing this technology in manufacturing. On the next slide, I show the simple function of how many squares can you get out of one of these circular wafers. That is, depending on the size of the square, and I'm measuring the size of the square here as the edge of a square die. That is, a 0.5 die is a ½ inch by a ½ inch. And if you pack those on an 8-inch circular wafer, you can get 220 or whatever that point is there on the wafer geometrically. It's not just a case of the ratio of the areas, and squares don't pack perfectly in a circle. You have to wiggle them around to see how it fits best. But this is a straight geometric relationship of how many square die of a certain edge can you get on an 8-inch wafer. The thing you see right away is that you get well over 4 times as many half-inch die as you get 1-inch die, which has to do with the efficiency of packing squares in a circle. Clearly, if what you're interested in doing is making a cheap piece of silicon, you want as small a die as possible because you want to get as many as you can. But this far understates reality because, in fact, not all the dice are good. If you look at the silicon wafer as containing some kind of a random distribution of defects, and should one of those squares include one of those defects, it's no good. We have to reject it. You can see that a bigger piece of silicon, a bigger die, has a higher probability of picking up a defect for a given defect density than a small one does. So not only do we get more of them to start out with by making them small, we get a higher percentage of them that are good. And I have done some calculations along that way on the next slide, showing the yield, that is the percentage that are good, for various die sizes, for various defect densities. Now, defect densities here are stated in average defects per square centimeter. Excuse my mixed dimensions. We use inches for die, centimeters for defects. It just happens to be the conventional units that we've grown up to use at Intel. And if I translate them, I lose some of the relations I'm used to being familiar with. Anyhow, this reflects a range of defects from probably something better than the best production processes today to something comparable with the worst, because any company that's beyond the 1 defect per square centimeter now probably is no longer in business. As you can see, these curves diverge quite rapidly as you go to the right. So the defect density is an extremely important parameter here, as is the die size in determining what we get. In fact, the next slide shows how many good die you get, where we combined the yield from the previous slide with the number of possible from 2 slides previous, and see the total number of good die one gets for various defect densities and various die sizes. Here we see that 7/10 inch die that I was describing indeed does give us about 3 die per wafer should we have the high density, the 1 defect per square centimeter in our process. But we might get as many as 70 or so die from the same wafer if we were operating at 1/10 of a defect per square centimeter. The factor of 20 difference in how many good units we'd get off a wafer, depending only on the quality of our processing as measured by defects per square centimeter. So there's a tremendous premium on low defects in the processing and in squeezing to the smallest possible die. Another way to look at this is cost. If I take those numbers of die off a wafer and reflect a cost of a processed wafer of something like $3,000, which is certainly in the ballpark, although I'm sure every company in the semiconductor business would quibble with it one way or the other. You see that it's very easy to get a die just from the processed wafer that costs over $100. Taking our 7/10 inch die again, in fact, you have to operate a very clean process, a low defect density, in order to keep the die cost below $100. On the other hand, if I could get the same function on a piece of silicon that was only a 1/2 inch on a side, I get down to a $100 cost, even with the poorest manufacturing, and something in the range of $20 with the very best manufacturing. So there is tremendous leverage in that direction. And that's the reason you see the kind of evolution you do in product lines. For example, On the next slide, I've shown photographs of 3 different generations of Intel's Pentium processor. The original one made on 8/10 micron minimum feature size technology. The one that was a workhorse in 1994, or most of 1995, the 0.6 micron technology. And the current one we're shipping mostly today, the 0.35 micron technology. The die size is about half the area in each of these. That is, the edge is the square root of 2 down in each case. So the 1995 die is only a quarter as large as the 1992 die. From that alone, we get 4 times as many off a wafer. When you take into account the improved manufacturing in the meantime, we clearly get a lot more than that. So the cost of one of these on the right is a lot less than the cost on the left. On the other hand, if you look here, you see that the maximum frequency is doubled. The 66 megahertz maximum we can get off the 8/10 micron technology. We now ship 133 megahertz devices. Twice the performance from that alone. The power has dropped a factor of 3. This is that violation of Murphy's Law coming in, where we've made the same device on 3 generations of technology and have realized the advantages of going to the smaller structure on the new technology. It clearly benefits in a single generation. And when looked at over several generations, the benefits are even more startling. On the next slide, I've showed Intel's entire family of 32-bit microprocessors, from the original 8386 to today's Pentium Pro. In fact, I've even shown some here that don't exist yet, particularly the last generation of Pentium Pro shown on quarter micron technology, since Intel has no quarter micron technology in production yet. This shows the trend, though. If you look at the first generation of each of the product families, you see that the area is actually increasing. The Pentium Pro in the first generation is bigger than the Pentium was in its first generation, even though it's on 1 generation later technology. Notice the size of the Pentium and the Pentium Pro, for example, both on the 3/10 micron technology. The Pentium is significantly less than half the size of the Pentium Pro. So what we've done is we've taken advantage of this higher density technology in 2 different ways here. One place we've taken advantage of it to make the same device lower cost, higher performance. In the other way, we've taken the advantage of the new technology to make a much more complex device, actually even somewhat larger than the previous one, but with the expectations of shrinking it onto at least 2 subsequent generations of technology. This is the power of this ability to continue to make smaller and smaller structures, and it's why the industry is driving so hard in that direction. Now, to do this has become increasingly difficult, and as it's become increasingly difficult, the equipment has gotten far more sophisticated and far more expensive. We've evolved from a very people-intensive industry to one that is very capital-intensive. I can show this a bit by looking at the cost of the equipment to build 5,000 wafers a week at various times, various generations of technology, where the minimum feature size is shown along the curve and the wafer size is shown along the top. I chose 5,000 wafers per week because that's about the size manufacturing facility that takes full use of the equipment, where you can balance the output from one type of machine with the next type of machine by having 2 of these and 7 of those or whatever it takes. So equipment typically doesn't have to sit idle very long. When Intel started in 1968, we not only equipped our first manufacturing facility, we developed our first products and processes all for $3 million. Today that doesn't buy a single production tool. In order to build a reasonably efficient factory at the 3/10 or 0.35 micron generation, You see, we're well over $1 billion for the equipment alone. You add that to a building that probably costs $300 to $500 million, and you see you're at a factory that is the order of $1.5 billion in order to have a reasonable, efficient manufacturing facility, and that's continued to grow. In fact, the growth to quarter micron is rather significant, and before long we have to consider another increment in wafer size. There's an industry trend toward 12-inch wafers instead of 8-inch wafers. If you look at previous changes in wafer size, for example, the change from the 1.5 micron technology to the 1 micron technology, you see the capital cost more than doubles. Similarly, from the 0.8 micron to the 0.5, which goes from 6 to 8-inch wafers, it doubles or so. I guess from this I ought to speculate that a 12-inch wafer facility in the next generation of technology, the equipment alone will be in the $2.5 billion range. This is really a capital-intensive industry. That's far more than a modern automobile assembly factory, for example. The reason is the cost of the equipment. Well, twofold. The cost of the equipment and the fact we're increasing the number of process steps in order to do all these nice things like add more metal layers to maintain the density. For example, the lithography equipment, the basic machine for printing patterns on the silicon wafer, has escalated in cost from $12,000 per machine when Intel got started to something like $10 million per machine for the 0.18 micron technology. And that's not a firm number yet. There's some speculation it might be closer to 15. The quarter micron technology, however, with about $7 million cost, is something that we're already spending to put the capacity in place. So from $12,000 to $7 million, a 500-fold increase in the cost of a machine to process about the same number of wafers an hour. The wafers are bigger. The quality of the process is a lot better, but basically you put about the same number through in a given time. Well, what can a fab turn out? The world market for personal computers is predicted to hit 100 million sometime later this century. It's something well over half that now, maybe 60 million plus last year and growing this year. We estimated what it would cost to build 100 million of the kind of personal computers that sold last year. For the CPUs, the memory products, the rest of the semiconductor products that go in there, and discovered it would take some 40 of these wafer fab facilities of the kind we were talking about. These are wafer fab facilities that we said cost about $1.5 billion apiece. So it requires about a $60 billion capital investment in order to make just the semiconductor devices for 100 million PCs. Who is going to invest this $60 billion? Well, a lot of people will. Another way of looking at it, though, is to look at something we call Rock's Law, Arthur Rock being one of Intel's directors from the very beginning. And he pointed out that the cost of processing a single wafer is growing exponentially with time as well. But who's going to make all these investments? Well, if we add up what people have spent over the last few years and what they are projected to spend for the next few, we see that the industry is willing to step up to this kind of investment. This is now a worldwide industry where the contributions from North America, Asia, excluding Japan, and Japan are all major contributors to the capacity. In 1995, the industry invested some $35 billion in capital expansion, and with the announced facilities in place, it looks like we will average in the $40 to $50 billion a year over the next several years, assuming there's not some major turnaround. This is a huge amount of money, and for a very capital-intensive business, what to be expected to add probably $1 in revenue for each incremental dollar spent on capital. That is, if we spend $40 billion on capital this year, the revenue ought to increment by $40 billion more or less, to make it a reasonable investment. So we can look at what's expected to happen in the growth of the worldwide market. This shows the projections from the official agency that collects this kind of data. And lo and behold, they are showing increments that are at least of the order of $30 billion anticipated for the market looking forward. This is a very large rate of growth for an industry of this size. Last year we were about a $150 billion industry, growing a very large amount in that particular year, and anticipating that this is going to continue. So we have the bits and pieces in place. I think the technology says we can continue to make considerable progress by working the same way we have. That we have a few more turns of the screws, generations of technology before we run across any real problems. The industry responds by saying we're willing to make the investment to continue to grow like that. So how concerned should we be? Well, I'm concerned more on the economic end, frankly, than I am in the technical end. I think we've looked at the technical limits long enough. We recognize we'll get to some eventually, but the cost of getting close continues to escalate. And then I look at the requirements and the continued growth of the industry here for us to make the progress we've made in the past by keeping our investment the same. And on the next slide, I've plotted that along with an estimate of the world's gross domestic product summed together. And just looking at semiconductors now, not even the finished products that incorporate semiconductors, and extrapolating the growth rate we've come to depend on, the 15% per year sort of thing, and you see that by about the year 2040, there is nothing but semiconductors. We're 100% of the world's GDP. Well, clearly that's not a very likely outcome. And I don't think it's very likely that the GDP will actually grow significantly as a result of our approaching it. I think the solution to this problem has to be a slowing in the growth of the semiconductor industry to leave room for some of the other things we need, like food and shelter, and clothing. In fact, I don't know what a maximum percentage would be, but on this basis, by something like the end of the first quarter of the next century, we would be 10% of the world's GDP, which also seems high. In fact, by about the end of this century, if we stay on this slope, we'll be 1%. And that's about as big as most industries seem to get before their growth slows dramatically. The auto industry got to a few percent at one time. Of course, we represent a subset of the electronics industry. I think electronics is such a fundamental capability in the information age that it might grow to, if not a double-digit percent, at least a large single-digit percent. But I don't think semiconductors can be more than a quarter or a third of that. So I think just the economy of the world is going to put some limitations on how fast we can grow. In the meantime, we can continue to enjoy the benefits of what is a phenomenal technology, one unprecedented in human history. For example, in your PC, just over the last few years, you can see performance advantages where it was $225 per million instructions per second in 1991. It's only $11 in 95, and we can look forward to $7 per MIPS this year. Nothing else gives you this kind of improvement with time. It's a technology that I think will continue to be extremely important, if not forever, at least for many decades looking forward. And I appreciate the opportunity to share some of my excitement about the technology with you today.